All right, hi there, and welcome to this recorded webinar. So we wanted to run this live last week, but we weren't able to, so we thought we'd just do a recording and share it around. So my name is Patrick Edwards, and I'm the Customer Experience Manager for Fond. My role is mostly helping new users get productive when using auto design. I work closely with all our users to learn more about their needs, and also work closely with the software development team to create software that's solving the problem of fibre to the X design in hopefully a simple way. So I've worked for Biarri for just over 4 years, and in that time I've used the software internally to create networks, and I'm now really excited to put that software in the hands of users from outside of Biarri to help engineers and planners be more productive. So this webinar aims to educate people on how to design, on how auto design works and what it needs, but also how it needs to work as part of a larger set of tools and processes. We'll see how we humans can guide auto design to create designs that are very useful. And as the title suggests, this webinar is about turning GIS data into fibre networks. And so we'll talk a bit about that data. Another important topic will be the rules that humans can set to guide auto design. So for a while, we certainly wanted to make auto design this super intelligent thing that could design any network. And that's pretty normal. We all want to make technology better. We want to make technology work for us, but it's also extremely difficult. And as we'll discuss, it's not really worth it after a certain point. We hear a lot about AI taking away the need for humans to make decisions, but we really won't see AI doing this for a long time. What we have seen and will continue to see, though, is AI supporting human decisions more and more. So while we're still improving our automation engines, we're spending a lot less time doing that and more time making it simple for automation to support planners and engineers. This is because a common criticism of auto design is that it doesn't know enough about the real world. So we're now coming up with ways for engineers to efficiently give auto design that crucial real world information. So while automation technology remains at the core of auto design, it doesn't stand alone. Humans need to be able to dictate their needs as well as their expertise to the automation engine. Strict data and rule standards allow planners to communicate their needs to the automation, and we define these in a way that's rigid enough for a machine to interpret, but flexible enough for humans to work with and be creative. So digital processes in collaboration enable planners to work on this together and pass data off efficiently between workflows. So this little anecdote here, I visited a customer recently to learn a bit more about how they were using auto design. Now we'll often use automation internally to create large-scale designs. I think my record is 1 million homes in a week. But we've been doing this for a while, and we're pretty well practiced at preparing input data and creating good workflows for large amounts of data. So I was really pleased to see a user who began developing their own workflows and methodologies for preparing data, and actually completed designs for almost 200,000 homes since starting to use Fond late last year. So this particular user, quite a smart guy, so I can't really be too surprised. But it was just a milestone for me and for the software development team, because it was the first time one of our users had made such an enormous progress on their own, and with very little effort really spent on helping them. So now let's just take a step back and think about the old way of doing things for a little bit. So a manual or semi-automated approach to auto design is difficult to scale. And while it's often the way to create the correct designs on the first try, as the size of the project increases, the effectiveness of adding extra engineers begins to diminish as no one is considering the global problem or following the same rules or objectives. For example, if we break a project up and hand it to 10 different engineers, we'll get back 10 different designs all done according to how that particular engineer thinks is best. And this subjectivity can create problems down the line. But just as that very manual approach with lots of people doesn't scale well, neither does just using automation on its own. So you won't get a very accurate design just by clicking a button. And for a while, we wanted to do that, but fibre design isn't an exact science. We tried quite hard to fully codify network design rules, costs, benefits, and the physical environment. But there are so many trade-offs and data points that just can't be communicated to the automation software, and so this approach won't work. What we've done instead is decided to keep auto design the center of a team. Everyone's able to provide input to that software. Things like architecture constraints should be controlled by planners. Designers and field teams must be able to incorporate feedback from the field. And geospatial data must be contributed from a variety of sources like write-out. Multiple stakeholders should be able to upload and edit the data that's going to underpin the design. What we know now is that automation on its own can only get us around 70 to 80% of the way towards a constructible design. It will get us within 10% error, but in terms of the amount of work that needs to be done, it'll get us 70 to 80% of the way there. To cover the rest of that distance, we need to make sure that humans can take control and carry it through to completion. So what I'm going to do here is jump over to our automation software fond and do a quick little demonstration. I'm going to demonstrate how we can get quite a long way with some very simple rules and simple data. So this is fond. I've just got a blank account here with no projects in it. I'll create a new project. Alright, so I'll give that project a name, webinar 1, and I'm going to select an architecture. So I'll talk a little bit more about architectures in a moment, but I'm going to use an architecture that's fairly common, where we've got a cabinet with 288 ports and connecting out to 8 port terminals or closures. I'll talk more about this architecture in a moment. For now, I'll just save that. The next step is I'm going to get some input data. The input data is going to determine where Fond is going to run the fibers to and the potential paths that it can take to run that fiber. I'm going to source the data using area select. And area select is a feature in Fond that we use to connect users with the data that they need to generate a design. So any patch on the map here is where we currently have data. Anywhere in the United States we can source data for. And that's just part of a subscription that users get access to this. So I'm going to jump in, go down to Illinois, maybe Monticello, or Monticello. All right. So to use area select, all I do is just draw a polygon, and this polygon just needs to surround the neighborhood that we're interested in designing, the neighborhood or the town. I'm just going to use a small section of Monticello at first. Alright, so we've got 464 homes in this little polygon. I've imported the addresses, but I've also imported the underground path, that's these orange lines. So once I've imported that, I'll draw the central office location. So this could be where we're placing the OLTs, but it could also be a tie-in point to the network, to an existing network. And now I'll go ahead and hit generate design. So what Fund's doing here is it's taking all of the address points and it's taking all of the underground path and it's considering all of the different ways that it can connect each of those homes back up to the central office via that cabinet through the 1x32 splitters. And it's following a set of rules to do that. It wants to minimize the total amount of equipment, but it needs to do that while maintaining that maximum drop distance of 750 feet, so that's the distance from the address to the terminal. No more than 8 homes per terminal, and then no more than 288 homes connecting back up to that cabinet, and that cabinet's got the splitters in it. So once it's chosen the location of all of those cabinets, it's going to connect those cabinets back up to the central office, and again it's going to try to do that in a way that minimizes the total amount of cable. And then once we've created the whole design, Fond will go through and count up all the different materials and come up with a little cost. So that design's now finished. So that was just a really simple design. This is the sort of design that will get you halfway there on the way to that constructible design. This design's good for a feasibility study, and the feedback we get is it's good for around 10% estimation. All right. So what I just showed was how to create a feasibility design. So all we gave to the software was the underlying data along with a basic set of rules. So that's fine for a feasibility design, but for a high-level design, we need to be able to give it more information. The engine needs more information, and often that information is given by fixing the input data. So in that example, I just used underground data. Often that's all that's available. Aerial, strand, and pole data isn't always available. And so sometimes street centerline designs can be a good way to get started. They can be used as the basis for a walkout guide or for estimating footage. And then you can use that design then to walk out and collect information on where your poles are. A common question I'd get just after doing a design like that is usually something like, can I use my own data or the data from a utility company or electricity co-op for a feasibility design? My answer is almost always yes. So data from co-ops tends to be quite good. If it does need to be cleaned, we try to give you the tools that you need to clean it. So you can usually do that yourself, but then we can also, you can use automation and scripts to clean it more quickly. But yes, generally that pole and strand data and underground cable electric data that you get from co-ops or utilities can be used for feasibility designs. And when that happens, those designs can be extremely accurate because the underlying data is already so good. So here's a little roadmap, I suppose, to getting from that feasibility design to a low-level design. So what we provided at first was the address data and the underground data, and if it's available, the aerial strand data and the pole data. To move on from a feasibility design to a high-level design, we need to give it an extra little bit of information. So we might take layers from different sources, we might preference certain paths, we might preference the location for certain hubs. All of that brings more reality, more information to the design. And then to get to low-level design, that's usually you'll get that information of a valid cable route or a valid node location once the field team has gone out into the field and inspected to make sure that the design is valid. So we can update the input data to reflect reality to improve the accuracy of that feasibility design. So part of the way of getting from a high feasibility to a high-level design is improving the accuracy of that input data. So this is particularly important even at the feasibility level in areas where the base data that's publicly available is incomplete. And when conducting feasibility studies in these areas, some editing of that base data is usually necessary, and that can be for aerial or underground path, or even the addresses being served. So auto design uses data as the source of truth, and it can't infer data or fix data like a human can. It's only as good as the effort you put in. So this is where we need humans. Computers will do exactly as you tell it to do. So the two maps above, they look almost identical. However, one map on the left, you can see, has an orange, actually the one on the right is correct. That's got the orange line that follows that road all the way around. The one on the left, you can see, is missing some of that orange line. So this is the underground path, and it's the only route that auto design can validly take. So now you can see the design that results from this. If I go to the next slide. So you can see that Fonda's just gone ahead and connected all of those homes to the closure on the corner. And that's because it didn't know that it could go around the corner on that road. We hadn't given it the underground path. So when inspecting designs with auto design, you sometimes come across errors like this, where some bit of road or pole is missing from the input, and that impacts the design. So this is why it's really important to have good GIS tools built into the automation, because it then gives users the ability to quickly identify problems with the input data and then fix that input data to create a valid design. So when I completed that design earlier, I skimmed over the architecture and what that meant. So I'm going to go over that in a bit more detail now. So for the basic rules, we use a fairly simple and abstracted set of terminologies to determine the rules around how equipment can be put together. So we refer to these tiers of cables as Tier 1, Tier 2, and Tier 3. So the Tier 1 cable is often referred to as the drop, and it runs from the Tier 1 closure to the Tier 1 hub. So we've got two rules for this tier: the number of ports on the Tier 1 hub and the length. So that the port rules we're describing here, and these are example rules, and then the length of the cable from the Tier 1 closure to the address can be specified as well. And again, these are example lengths. We can include any length there that we need to. So as I mentioned, Fond will try to minimize the number of these closures, but it needs to do that within these rules. So the minimum number of closures in a design would be 1, but as we can only connect 4 addresses to a closure, if we were to use a 4-port size, that changes the way that Fond will go about connecting addresses to closures. So above the tier 1 tier is this tier 2 tier. So the tier 2 cabinet it's usually the location of the primary splitters in the design. And then the tier 2 cable is running from that cabinet to the closure. And we can set the sizes of cables that are valid to run between the cabinet and the closure. And we can also set the number of ports available on the cabinet, as well as the split ratio that's inside that cabinet. So this size here determines how many addresses can connect back to this cabinet. So auto design, it's going to try hard to minimize the number of these cabinets. So what we could also do is specify a percentage of spare to be left at that cabinet. So we might say always leave 10% of the ports free. And so Fond will minimize the number of cabinets while also allowing there to be some spare for future growth, potentially. So in a centralized split architecture, you might place a 1x32 splitter at this cabinet. You could create a distributed cascade split by just placing a 9 1x4 splitters in the cabinet and then using a 1x8 splitter in the tier 1 closure. Or you could just put the 1x32 splitter in the cabinet to have a centralized split design. And yeah, again, we can set the cable sizes that are valid for the tier 3. So that's the cables running between that central office location or the tier 2 cabinet. So those rules that I mentioned will get applied across the whole design, and you can see that. So I've got 2 designs here. The one on the right, we've used a 288 port cabinet, and the one on the left, we've used just a small 32 fiber, basically a closure with a splitter in it. And so you can see the result there is that the tier 3 cable has to push a lot deeper into the network as the splitters are more distributed across the map. And so you can see here that the one on the left has got a lot more of those green triangles within the hexagon because those cabinets have got much less capacity than the one on the right. They've got 288 ports. And you can also see a difference when at the tier 1 level. So the tier 1 closures on the left have only got 4 ports versus the one on the right have got 8 ports. Both have got a drop length of 750 feet. So in the areas where there's lower density, you can see that the design looks basically the same because the design is being constrained more by the drop length. But in the denser areas, you can see that there are a lot more 8-port closures that are being used as opposed to 4 over here because the drop length is having a lower impact than the port count is. So now that I've explained the architecture a little bit, I'm going to jump back into the demonstration and we're going to iterate on the design. And we're going to iterate on the design and under an imagined scenario where the field team has identified some new demand to serve. So let's say that the field team's gone out and done an initial inspection of this design, and they've noticed that there's this section of land out here that's going to be used for a subdivision with perhaps 30 homes in it. So what we can then do is say to Fond, this isn't just one point, this is actually going to serve 32 homes. And so I'll hit save. And so that value now is then 32. So what that is telling Fond, we're giving it the information to say, make sure you leave enough fiber for 32 demand points. Everything else has got a default of 1. And let's say we do the same thing over here. Let's say that the field team found that this wasn't just a single home, it was actually a quadplex, and so it's got 4. There are actually 4 little units in that particular land parcel. So I'll save that, and now I'll update the design. So that's going to go back through the design again, and follow the same rules as before. So it's using the same drop length of 750 feet. It's using an 8-port closure again. So the same rules, and it's also using that 288-port cabinet. But the design is going to be different this time because we've added new information, we've added new demand to the network. So what we'll expect to see here is this tier 1 closure actually serve this demand point with 4 drops rather than just 1. And down here we'll expect to see the tier 2 cable extending much further to create a dedicated demand point that's going to serve this future demand that we've reserved. So we'll just give that a moment to run. And while that's running, I might just point out that there's a few other things we might want to change with this design. Looking at the satellite, or looking at the map, we can see we've got these railroads through here, and you can see the design is crossing it at 1, 2, 3 points. The drops are crossing over as well, but in reality we'd probably just delete that point if it's on the other side from there. So it's crossing the railroad at 3 different points. So what I'll probably do after this is run through is influence the design a little bit more to remove those crossings, because we wouldn't want to be crossing that at more than one location. So I'll just let the design finish. And alright, so because we're recording, I thought I would just cut out about a minute of silence there. So but that took about another 3 minutes to run. So now you can see that this demand point here now has got a larger cable, a 24 fiber cable that's running up to this point with some reserved fiber. So this fiber, it'll be unsplit, so that's why there's only a 24 cable needing to run to that. It'll run unsplit fiber, and then we can split there a little bit later. And then up here, we can see this this address with a value of 4 is being served by this closure with seven demand points. And if I turn off this, we can see that 7 is made up of 4, 5, 6, 7. So that's 7 out of 8 ports are being served, 4 of them being served, serving this address point here. Alright, so I'll jump back over to the presentation now. Okay, so now I've iterated once. That gets us a certain amount of the way of the construction. What I'm going to do now is actually iterate again. So what we did earlier, we added some new address points to the design. So the scenario now is that the field team's gone back out and they've said these cabinets are in the wrong location. So if I go back to this design, we can see here that this cabinet is, we've placed it here, but the field team might make a recommendation to actually move it further down the road, perhaps to use less of this tier 3 cable. So what I'll do is I'll just move this cabinet to that location there and finish. And then some of their feedback might have also been around the tier 1 closures. So as an example, let's say that they wanted us to move this tier 1 closure away from the intersection. So I'll just move this tier 1 closure further down the road to here and hit finish. So we'll just keep an eye on where they are now, and I'll hit update now, and that'll regenerate the design. So it's regenerating the design, and it's using those same rules as before. So it's making sure that there's no more than 288 homes to each cabinet. The drop length is staying 750 feet, and the capacity on those T1 closures is still 8 ports. But now Fond has more information. The information is that the best location for the tier 2 cabinet is here, and that the best location for this tier 1 closure is down the road at this location, not on this intersection here. And it's able to run much faster because we've already told it where we want to place the cabinets and the closures, so it doesn't need to make that decision. The only decisions it's making now are on the routing of the cables. And so now we can see that the tier 1 closure is now placed here, and the tier 2 cabinet is placed up here, which is where we wanted it to be. So we've taken some information from the field and iterated on the design to make it more correct. So gradually this design has gone from being a feasibility design to something that is approaching a high-level design. All right, back to the presentation. So yeah, as I mentioned, that is about that'll get you about 70-80% of the way there to a constructible design. So in what I've shown you in the tool today, that's sort of it for auto design in terms of creating a design that's as correct as possible. So of course, to get to that point, we would have needed to make more adjustments to the design than I showed. But for an area of around 3,000 homes, that's usually possible in a few days to make those sorts of adjustments and then the iterations that you need to do. So what comes next to the final adjustments? Perhaps during a construction, and then the addition of splicing information and other construction documents like construction packs. So automation can be used to accelerate the development of splicing diagrams and construction packs, but at this point, automation has made the design as correct as possible in terms of the layout. So in order to take the design to the next step, we need to be able to export it to a third-party tool like a fiber management system or a database of records. So as an example, I'm going to export it to QGIS. QGIS is free GIS software that we use a lot. It's fairly powerful, and it's a really good tool to use as your. I'm going to download this again. Really good tool to use to. It's a really good tool to use for preparing geospatial data, but also viewing data if you want to view the data in more detail than Fond would. So download this design, and you can see it's styled in a fairly rudimentary way, but the point I'm really trying to make here is that you can export the design. It's really important to be able to export the design from your auto design tool to a third-party tool. So it sort of speaks to one of our aims, which is to make it possible to export data from our automation software into a number of different other fiber management systems or a database of records that could be used to manage the construction of the design and manage the future maintenance of that system as well. So that's really it for the webinar. Hopefully what you've taken from this is that with some basic data and rules, you can provide automation can provide a really useful design. It's important to update the input data, and that's important even for feasibility studies. Being able to edit the design is important, so we're trying to give control back to the engineer. And then once the design is correct, adding detail can be done later and then sending it out for construction. And finally, it's really important for designs to be exportable into other systems for construction and maintenance. Automation will get you to a correct design, but it then needs someone to live and be maintained over time. So, if this were live, we'd probably have some questions coming through right now, but since it's recorded, I'll just ask you to send through any questions you have to my email that's displayed on the screen there, patrick.edwards@biarri.com. I'll do my best to answer all of them over the next few days. So yeah, thanks so much for listening. I hope you learned a few things at least and feel more ready to use auto design in your own work.